Okay, so our next speaker is Tom Mansion, a junior security researcher from Quark's lab. So Tom is a passionate CTF player who really enjoys heap exploitation. He will be giving a talk about S.H.I.E.L.D, Scudo heap implementation exploits, leaks, and defenses. Let's welcome him on stage with a round of applause.
All right, so hello everyone. I'm happy to present my work on Scudo, the hardened memory allocator for Android, and I hope you all enjoy this presentation. So first, a quick introduction. My name is Tom Mansion, actually. I work at Quark's lab in Paris. I'm an Android security researcher, and I really enjoy CTF, so I thought I would look into the memory allocator on Android and see how it compares to another one I know quite well, the GNU C library allocator jemalloc 2. So first, a quick introduction on the heap. So what's a heap allocator, right? It's a dynamic memory management runtime that lives in libc. It's called by almost every program, and it's used very often, so we need it to have certain properties, right? So if we look at the properties of a good allocator, it has to be transparent. The developer shouldn't have to care about how it works, just need some memory, get it. It has to be reliable, use all the time, so it cannot fail too often. It has to be efficient. Memory is a resource. We don't want to waste it. Very importantly, it has to be fast. And sometimes it has to be secure. We'll see in this presentation that Scudo is pretty secure in most cases. But before diving into the difficult things, we'll talk about another allocator, jemalloc 2, which is much more widely known. And this one isn't very secure. So a quick refresher on how jemalloc works. This is going to be a high-level overview to not bore you with all the details, but it should give everyone an understanding of how it works and how it can be exploited. So when the heap is initialized, so on the first call to malloc, so memory is mapped for the allocator, and all of it is free to be used. We see here there's some memory that's reserved for the allocator, but we don't care about that. This uninitialized memory is called the wilderness, in red on the drawing, and the allocator keeps a pointer to the beginning of this wilderness called the top chunk pointer. So what happens when you malloc? So basically, you're gonna increase the top chunk pointer and return a pointer into this blue chunk to the user. If you want to allocate another chunk, say of a different size, like the exact same thing happens here. We don't have any free chunks, so we're just gonna take another chunk from the wilderness and return it to the user. So we can already see some important properties of the allocator here. One of them is that chunks of different sizes can be adjacent in the heap. They live in the same memory region, even though they get handled quite differently. Another property that we don't really see here is that the allocator is deterministic, right? So no matter how many times we run a program, if we make the same allocations in the same order, the heap layout of the program will always be the same. So what happens when you free a chunk? So let's say we want to free chunk B. Since it borders the wilderness, it's very easy. The allocator simply decreases the top chunk pointer and return the chunk B to the wilderness, right? So we return to the state. But if we want to free chunk A, chunk B is in the way. So this case is a little bit more complex. So we want to mark this chunk as free. And the way jemalloc does this is to store it in a free list, right? So the idea is that the allocator keeps track of free chunks by storing their addresses in linked lists. There are different types of lists for chunks of different sizes, but the idea is always the same. When we allocate a new chunk, we're going to first look into these lists to see if a free chunk can satisfy our request. Very important property is that these linked lists are stored on the heap itself. The user data part of the chunk, so the part that's right after the header, is reused when a chunk is freed to store pointers to the previous and next chunks in this list, right? So now we'll talk about exploitation. So there are different types of heap-based vulnerabilities that can be exploited, that can be used to exploit the allocator itself. So we'll talk about a few. So in the case of a buffer overflow, the first thing we have to wonder is what can we gain control over, right? So in the case of a buffer overflow, we can have a buffer overflow into a in-use chunk. This is not really an attack on the allocator itself, so we don't really care about that. But we can gain control over user-controlled data, right? So sometimes it's enough to exploit a program. And yeah, so when we overflow into a free chunk, then we can gain control over the allocator metadata, right? So these free list pointers, and the point is to corrupt these free lists, right? Our goal when exploiting an allocator is usually to create arbitrary chunks, so to get the allocator to return us a chunk at an arbitrary address. Just a quick slide to remind everyone how these free lists work. The most free lists, except for the Tcache, but that doesn't matter, the head of the list is stored in libc, and the rest of the list is stored on the heap, right? So if I manage to corrupt a pointer from chunk A to chunk B, let's say, if I write an arbitrary address, sometime afterwards, when I allocate a new chunk of the same size, I will get a chunk at this address. This is a bit of a simplified view, but I think it's enough for understanding how it works. So now let's talk about the real focus of this presentation, Scudo. So Scudo was built with security in mind. It's not only performant, it also attempts to mitigate a bunch of vulnerabilities. It's been the default allocator on Android since version 11, but it's also usable on other platforms like Linux and Trusty, the secure world OS from Google. It's based on an allocator that was developed in the LLVM project, but has since been adopted and is maintained by Google. So first we'll start by talking about its security principles, then we'll dive a bit deeper into the internals and talk about the building blocks that make it secure. Finally, we'll talk about exploiting this allocator, right? So the first security principle of Scudo is to separate allocation classes. The goal here is to limit the interactions between chunks of different sizes by storing them in different places called regions. It also prevents heap messaging, which leads us to our second properties to introduce randomness wherever possible. So Scudo randomizes the order of the allocations. So unlike in libc, when you allocate two chunks one after the other, they're not going to be adjacent in memory, right? And this is also to prevent heap messaging or heap feng shui. And it makes it harder to guess what we're overflowing to in the case of a buffer overflow, for example. Then another property is to protect the chunk headers with a checksum. This prevents small buffer overflows, right? So we cannot overwrite the header of another chunk if we cannot compute this checksum. And this checksum is based on multiple things, including a global secret that's stored in libc. Lastly, Scudo removes almost all metadata from the heap itself. We saw that in GLIBC and in many other allocators. That's usually the main problem. We can corrupt this metadata, and Scudo tries to avoid this by removing this metadata from the heap. All right, so now for the building blocks. Scudo is separated into two allocators. There's a primary allocator that serves most allocations, so the small ones, and then the secondary allocator that serves larger allocations. For the primary, as we said before, chunks are split into regions. Each region can only hold chunks of one specific size. The primary has a local cache that is used for everything, so basically every allocation and every deallocation will go through this cache. When it creates chunks, it puts a primary header in front of the chunk. We'll see what that looks like afterwards. And then the secondary allocator uses mmap to allocate larger chunks. There's a similar functionality in GLIBC. It also has a local cache, but this one is only for storing free chunks. And so when we allocate a secondary chunk, we first look in the cache to see if we can satisfy a request. Then the secondary allocator also uses the primary header, but on top of that, it adds a secondary header. So we'll see that in the next slide. In parentheses here, we see that they both have a quarantine cache. I put it in parentheses because actually it's not used in production builds because it's too much of a performance overhead. But the goal is that when you free a chunk, instead of putting it straight to the local cache, you put it first in this quarantine zone where it's going to live for a while and it doesn't get allocated again right away before promoting it to the local cache. But it's too expensive, so we didn't use it. This is what the chunk headers look like. So for the primary allocator, we see we have the class ID, so the ID of the chunk, which region it belongs to. The state, which says Is it allocated? Is it free? Or is it quarantined? The other fields, we don't care too much about them, but then there is the checksum, right? This checksum is computed using a CRC32 algorithm based on the contents of the header without the checksum, the address of this header, and a global secret that's stored in libc. So for the secondary allocator, the first two fields look a bit weird, right? We see these prev and next pointers. Actually, they're not free list pointers. They're actually pointers to in-use chunks. So the secondary allocator keeps a linked list of chunks that are in use for multiple reasons. Then we have the commit base field, which actually represents the address of this secondary allocation. Since it's allocated through mmap, it's going to be placed at a random address. We store this address in this field. Then we have the size, mmap, we don't really care about it. And afterwards, we have the primary header as well. So note that only the primary header is protected by a checksum. The secondary header isn't. Next building block is the regions we were talking about. So this is in the primary allocator. So there is one region per chunk size. So when the primary allocator is initialized, it will reserve a big chunk of memory through mmap before dividing it into 32 regions. Each region will actually start at a random offset of 1 to 16 pages from its beginning, and the gaps between the regions are called guard pages. These guard pages are just memory pages with 0 permissions, so any attempt to read or write into them will trigger a seg fault. So this is done to prevent huge buffer overflows that would spill into a neighboring region, for example. Guard pages are also used in the secondary allocator, so when we mmap a set of pages for an allocation, we'll surround them with guard pages. That's it. Then for the local cache of the primary allocator, it's basically a free list implementation, right? The big difference is that it doesn't live on the heap, right? It's only stored in libc, it's just an array. It's also called a per class because there is one per class of allocation, right? Each region has its own local cache. And as I said before, all allocations are made through this cache. So when it's empty, it has to be filled up. When it's full, it has to be drained. These drain and fill operations use transfer batches, and we'll talk about them in the next slide. So there's actually a second caching layer in each region. You can see the local cache kind of as an L1 cache for fast access, right? And the free list, you can kind of see it as a L2 cache. So this is the free list info that we see here at the bottom of the diagram. It's slower to access, but it's only used to refill or drain the L1 cache. These operations employ transfer batches. Transfer batches are simply arrays of pointers that live in a special region of the primary allocator, region 0, that we can see here. This region is only used for storing these objects and cannot be used by the user of the allocator. So you cannot allocate into region 0. It's important to talk about these transfer batches because they play an important role in introducing randomness to the allocator. We'll see exactly how that works now. So here we have a scenario where there are chunks already allocated in region 1, but its local cache is empty. So if we want to allocate more chunks, we have to refill the cache first. So the way Scudo does this is by carving out a big block of memory right after the end of the already allocated chunks and dividing it into equally sized blocks. So there's only one size of chunk per region, so we know the size of the blocks. Then a transfer batch will be allocated to store pointers to these chunks. But before copying the pointers over to this transfer batch, the allocator will shuffle them. And this is where the randomness is introduced. So once the transfer batch has been created, we can copy some of its pointers over to the local cache. We want to keep some pointers in the transfer batch ready for later refills of the cache. This is why we can see it as a kind of L2 cache, right? This is a bit of a simplified view, but I think it's enough to understand how it works. Final building block is the support for ARM MTE. MTE, so the memory tagging extension, is a feature on ARM SoCs that's been introduced in ARM v 8.5. The idea is that you're going to use the higher order bits of a pointer that are actually never used when storing addresses to store a key, while tagging the actual memory with the same value, called a lock. So in the case of a buffer overflow, the pointer that's used to write into memory will only have the correct tag for its own chunk, and as soon as we attempt to write into another chunk with a different tag, a mismatch will be detected and the program will be aborted. This is very efficient for detecting memory corruption vulnerabilities, and Scudo has been built to support it. For each allocation, Scudo will assign a tag to the chunk's header and a different tag to the chunk itself. For secondary allocations, there's a different tag for the primary and secondary headers, right? When a chunk is freed, the memory is retagged, and this completely mitigates use after free vulnerabilities. This is also why the quarantine is disabled, because this mitigation completely supersedes the quarantine, so it's of no use. MT is not yet fully implemented in most phones, so we can start to see some support for it, but it's not widely adopted yet. So now for Scudo exploitation. First, we'll talk about use after freeze. This is not really an attack on the allocator itself, so we'll keep this brief. But basically, without quarantine and MT, Scudo doesn't mitigate use after freeze at all. But there is no inline metadata on the heap to corrupt, right? So the target is actually the program itself, right? We want to do some type confusion attacks and that kind of stuff. So this is an example from a CTF challenge where we do a type confusion. It's actually a 32-bit challenge that we ported to Scudo, very basic, but the idea is that you want to call this bring back the flag function, which you cannot by using the program normally. You're going to do a type confusion to write the address of this function in the slot for the bark function, which you can actually call. Anyways, now for actually exploiting the allocator. So in this section, we'll talk about two exploitation techniques that have been published recently, forged commit base and safe unlink. But first, we have to talk a bit about Zygote on Android and how it kind of breaks the security of Scudo. Finally, we'll talk about patch to the second technique, but don't be discouraged because we'll also talk about what we can still do after the patch. So these two techniques we're going to talk about were published recently by researchers over at EPFL in Switzerland. I really recommend reading this paper, it's great. Basically, they introduce the techniques we're going to talk about and they demonstrate one of them by backporting an old CVE to Android 14 and exploiting it with the forged commit base technique. So both of these techniques, they share kind of heavy prerequisites, right? You need to be able to guess the address of next allocations, and you need to be able to forge a checksum. And both of these, you cannot really do them in a regular context, right? But do they always work? And no, they don't. On Android, we have this little thing called Zygote, which is pretty useful, especially on lower-end phones, but has proven time and time again to be a security risk. You can see it as kind of like a mother process that gets forked to spawn other processes. So when Android's user space boots up, the init process starts a bunch of daemons, and then it starts Zygote. This process loads a bunch of framework code and resources into its memory space. And so when you start an app on your phone, instead of having to load all of these again, you just fork this process and you already have them in your memory space, right? Great, but what can go wrong with this? We said before that Scudo tries to avoid storing metadata on the heap itself. Instead, it stores all of it in libc. But the problem is that Scudo is initialized by Zygote, right? So basically what it means is that the forks of Zygote will get the same addresses for their memory mappings as Zygote. So regions will be mapped at the same address. The seed that's used for randomness will actually be the same in all Zygote forks. And the security cookie for computing checksums will be shared. So in fact, let's say that app A is trying to exploit a heap bug in app B, right? They're both forks of Zygote. App A can guess the addresses of allocations in app B simply by making the same allocations in the same order and looking at the addresses of the chunks it gets back from the allocator. So it can use itself as an oracle, basically, to predict the allocations in the other app. So if we go back to our prerequisites, we can see that they're met now, right? Because the random seed is initialized by Zygote, the security cookie as well, and the memory mappings are the same. So basically, we can predict chunks addresses and we can forge checksums. So that's great. Now we can exploit Scudo. So the first technique is called forged commit base. The idea is that you want to force the secondary allocator to return one arbitrary chunk. And as the name implies, we're going to target the commit base field in the secondary header. So what we're going to do is actually forge a fake secondary header. If you remember, secondary headers go on top of primary headers. So we can actually do this in the primary allocator. There's a few more constraints. So the first two we know that they're met, but we need to be able to write hex 28 bytes before a chunk. So basically we need to have a buffer overflow. We need to be able to free the victim chunk, and we also need to have a secondary chunk that's already allocated to set the count of allocated chunks to 1, basically. So how it works is we start with a buffer overflow, right? We know the address of chunk B. We overflow into it from chunk A. And then what we do is that we forge a fake secondary header above chunk B's primary header. And in this header, we're going to set a few fields. So the prev and next pointers, we set them to 0, but this is just to pass some checks. Then the interesting field is the commit base field. We set it to the address of our target, so where we want our arbitrary chunk to land, because basically when you free a secondary chunk, Scudo will read its header, take the commit base address, and store that address in an array, and then later on when you allocate another secondary chunk, it will just take the address from that array. Well, for the rest, it doesn't really matter, but we have to also modify the primary header to set its class ID to 0, which is the class ID of secondary chunks, and thus we have to be able to compute the checksum again. So once we freed this chunk B, the address of target is placed in the secondary cache. Next allocation in the secondary allocator will return a chunk at this address, and we can profit. So this is quite basic, but the next attack is a bit more complex. So the idea of this one is to force the allocator to return a chunk that overlaps the local cache. And this is very powerful because once we have a chunk that overlaps the local cache, we can basically control all subsequent allocations, right? This time we're targeting the prev and next pointers in the secondary header. Which, as I said before, are pointers in a linked list of in-use chunks, right? We need a few more constraints for this exploit. We need a buffer overflow like the previous one, but we also need a controlled free primitive, right? So we need a pointer that we can mess with and call free on that pointer. We need to be able to call this primitive 3 times, so there are also quite heavy prerequisites. So how does it work? We start with the buffer overflow, same as before. Then we're going to forge a fake primary header that's a hex 30 bytes before the victim. And then we're going to use our controlled free primitive to free that fake chunk, right? This will effectively place the address of the fake header in our local cache. Step 3 is to repeat steps 1 and 2. This way we have the address of our fake header twice in the local cache. Note that Scudo doesn't check that this address is already in the cache, doesn't really care. Step 4. We're going to forge a fake secondary header. And this time we're going to put the address of the first element in our local cache in the prev and next fields. And this is to set up an unlinking attack. So if you're familiar with GLIBC exploitation techniques, you should know kind of how it works. But next step is to free the victim chunk, trigger the unlinking. So here, just a quick reminder of how unlinking from a linked list works, right? We're gonna remove our chunk from the linked list or set our next chunk's previous pointer to our previous pointer, our previous pointer's next pointer to our next pointer. Basically, if you follow the code here, you will see that what happens is that we put the address of the local cache inside the local cache itself, right? So then the next allocation will basically return a chunk that overlaps this local cache, and we get control over all subsequent allocations. So this is quite powerful. Unfortunately, it's been patched. It's been patched by the introduction of compact pointers in the local cache. So the compact pointers, you can just see them as, instead of storing a raw pointer in the cache, we're going to just store the offset from the beginning of the region to this chunk. And this breaks not only step 5, but also other chunks of the exploit, right? Because if we go back, when we do our first 3 steps, instead of having the actual address of our fake header in the local cache, we're going to have a compact pointer, so an offset, which is going to break the unlinking at this stage, right? The linked list will be broken. We cannot perform this anymore. So that's sad. But what if we skip the unlinking step, right? What if we assume that we can get a chunk that overlaps the local cache in some region? Maybe we can get to this by using the other technique, forge commit base. Maybe some other techniques will come out in the future and we can use them. Right. The thing is that when Scudo allocates from the cache, it doesn't check that the decompacted pointer stays within the bounds of a region, right? So basically, when we have control over the local cache, we have control over this compact pointer variable. But if we can get control over this base variable as well, we have the same primitive as safe unlink, right? We can allocate as many chunks as we want at arbitrary addresses. So actually, this is doable. If we assume that we have control over the local cache for region 2, right? We have this region2.base variable that's stored in the allocator metadata that's in libc. We can compute the distance between this base and the metadata that's in libc, and store this distance in the cache itself, right? Then the next allocation will return a chunk that overlaps this allocator metadata. Then we can change the variable, the region2.base variable, which will give us control over everything we need to make arbitrary chunks. So then we get the same primitive as safe unlink without using the unlinking. So as a conclusion, on Android, Zygote forked processes can attack each other quite easily. One of the two techniques I've presented was patched, but if we combine the two, we can still get interesting primitives. Just as a reminder, in other contexts, when we're not in the context of Zygote forks attacking each other, Scudo is still pretty secure, right? There's a lot of security mechanisms that are there to make exploitation harder. For the future, there's not much left to exploit, right? Or basically all the interesting fields in the secondary header have already been kind of exploited. And anyways, when ARM-MTE will become more popular and implemented in more phones, almost all of these memory corruption vulnerabilities will kind of die. So yeah, that's a bit sad, but thank you anyways. I think there's quite a lot of time for questions. Yes. Right. So okay, right. So ARM-MTE is already deployed on some phones on Pixel 8 and Pixel 9 devices from Google. You can turn it on kind of as an experimental feature. I'm not sure of the exact state of MTE. I know it's already being used in these very recent flagship phones, but on the majority of the smartphone market, MTE is not really available. So if we go back to the slide about MTE, I can explain a bit more how it works. Right. So yeah, the idea is that we're gonna store a value in the higher order bits of a pointer, right? And these higher order bits are actually never used because the pointer is 8 bytes. You don't need all of those bytes to store an address. So you can actually use these higher order bits to store this tag, and then in the memory we're going to store the same tag, right? And so when you're using a pointer to access some memory, there is some hardware instructions that are going to check that the tag matches the lock that's stored in memory, right? So basically, if you try to do a buffer overflow, you have a vulnerability that lets you do a buffer overflow from the orange chunk here into the blue chunk. You're going to use this orange tagged pointer, right, to write into this buffer. And so as soon as you try to write into the next buffer that has a different tag, the mismatch is detected and the program is aborted.
All right. So are there any other questions? Okay, so if there are no other questions, thank you so much for the talk. Let's give him a very warm round of applause.